So, hello to everybody. Thank you for joining us for this evening's History Study Group lecture. Tonight we're joined by Peter Debney of Arup and Oasis Software. Peter has also recently authored the iStruct's computational engineering book. Peter's talk this evening will focus on the digital design of the Sydney Opera House as the first use of finite element analysis and parametric design. So welcome, Peter.
Thank you very much.
I'm going to mute everybody now, which may mute you too, but then I will quickly try and unmute you.
Oh, I can unmute myself. Excellent. You can still hear me.
Perfect. Thanks,
Excellent.
Peter.
All right. Welcome. Hello, everybody. Sydney Opera House, 50 years on. Straight speaking, that's 50 years from well, it was 58 years. The opening, the award of the iStruct Gold Medal or Supreme Award, whatever it's called. I think some of the terminology has changed over the years. But anyway, yes, structural analysis and design of the roof and the glazed walls. An aspect, yes, glazed walls, people forget. The roof gets all the interest. Okay, so yes, the Sydney Opera House. Got a wonderful quote here from Uwe Arup and Jack Sons. So he said the difficulty with writing anything about the Sydney Opera House is to know where to begin, what to include, and where to end. There is something for everybody. It is all things to all men. It is a dream that never was, a structure that could barely be built, an architectural tour de force, a politician's nightmare, a population's talking point, and much, much more. It is not so much a building as a controversy. Well, they wrote it back in 1969. I mean, these days it's fair to say I think everybody knows about Project 111200. It was a great design that didn't work. The construction started years before the design of the superstructure was finalized. They lost the architect, nearly lost the engineer too. Yet changed from being an eyesore to an icon, resulting in gold medals for Arup, both personally and as a company, but also most interest to me. Yeah, there's a quiet revolution in the basement of Arup London. So the story of the Sydney Opera House starts in the late 1940s. At that point, there was no major concert hall in Sydney, and Charles Moses, who was the general manager of the Australian Broadcasting Commission, realized that that situation had to change. He enrolled Eugene Gosens, who was the distinguished conductor of the Sydney Symphony Orchestra, and also Joe Cahill, who was the Premier of New South Wales at the time. Together, they identified the site, Bennelong Point, which you can see in the aerial shot there. And this was a promontory which at the time was holding disused tram sheds. Also, to note, as I discovered recently, Bennelong was an Aboriginal chief who became a significant person in that he was one of the big the people who established communications between the Aboriginal Australians and the British, and Bennelong Point became his home. So what was the requirement? The project requirement was two main halls, one holding 3,000 to 3,500 seats, and one holding about 1,200 seats. And the design requirement was concerts first, followed by opera, then ballet, and so on. Yeah, interesting note, it wasn't intended to be an opera house, it was intended to be a concert hall. Now, they set up a competition, and that was won, so international competition, it was won by Jörn Utzon, And despite, his original design was actually, well, he was initially rejected by the design committee. Um, well, he was initially rejected by a subset of the design committee. The committee hadn't fully met, but when the full design team met, um, they actually brought his design back out of the reject pile. So his original design, vision, and so on, it was concept of sales. This is one of his initial scheme design submissions. And yeah, um, there was a lot of controversy even at that point, as the assessor's report said, the drawings submitted for the scheme were simple to the point of being diagrammatic. Nevertheless, we have returned again and again to the study of these drawings, and we are convinced they present a concept of an opera house which is capable of becoming one of the great buildings of the world. We consider this scheme to be the most creative and original submission. Because of its very originality, it is clearly a controversial design. We are, however, absolutely convinced about its merits. Now, note at this point, the design was submitted with no structural input at all. It was purely these architectural sketches and plans. And his design had the two main halls side by side. Now, unusually, most of the other designs were focused more on the more conventional access routes. So remember, it's on the promontory, and people would arrive from Sydney, and the usual plan for a opera house or so on is to enter through the front. You have a you know, reception atrium area, and then you go into the halls, and then at the back of the halls, there's then the fly towers and all the various services and everything. It's on a different approach. He realized that the location was important, and he wanted the opera house to actually reflect and be a part of that location. So yeah, he has two main halls side by side, and the public access is around the sides of the hall. So you still enter from Sydney, you go either side of the building, then enter from the halls from the far end. So when you're there, you remain in visual contact with the Sydney Harbour the entire time until you actually go inside the concert halls. It's also meant the fly tower, where they hang all the scenery and so on, are then hidden in the middle of the building underneath those very high wings. So the reason for the height is actually quite functional. Now, in addition to the main halls, there were multiple small halls, rehearsal rooms, restaurants, and so on. And Utzon was appointed in 1957. Now, Utzon was Danish over Arup, also Danish, and Arup is over. I never quite get the Danish pronunciation right. Let's go over Arup. So Ove, he was very passionate about modern architecture, and he was very keen to actually get this commission. And he, in fact, he personally pursued Utzon, use their sort of common Danish heritage to win him over and persuade him that Arup, or Arups, as the company name was, well, description of the Arup. These days, we're not allowed to say Arups, but in that time, I think they used Arups to refer to the company, and Arup to refer to the person. So yeah, Arup persuaded Hudson that Arups was the company to work with, and yeah, the original design was unbuildable, and so the challenge was, can they find a structural design which could still maintain the architectural intent? And picture here, you see Jørn Utzon on the left, over Arup on the right, and Paul Arm in the middle, who became one of the sort of the lead structural designers on this. Well, in the process of finding the design that worked, there was much controversy on routes, so many iterations of the route. Now, politics played a major part of this project. So Joe Cahill, the New South Wales Premier, he knew as a politician his time in office was limited, and so he insisted that construction work started as soon as possible. In fact, before there were even drawings, because he wanted to prevent subsequent political leaders from cancelling the project. And yeah, so Sydney Opera House started on site in 1959. This was so this was 5 years before the superstructure design was actually finalized. And in fact, um, yeah, the foundation design was actually finished. Foundation construction was finished in the same year that the roof designs were actually determined. Geology of the site was open jointed sandstone, or the range of hardnesses, so quite soft to quite hard, with seawater percolating all the way through. And so the geotechnical team had to come up with a foundation design which worked whatever went on top. So apparently this involved over 700, 900 diameter piles, or 3-foot diameter piles. And yeah, the roofs went through so many iterations, which we'll cover in a minute. Now, yes, politics. These are some of the newspaper articles from the time, and it got to the point that Utzon left in 1966. I mean, it was a time when he was being asked to produce drawings for the interiors and glass walls and so on, which apparently he didn't want to, but also there was a lot of political pressure, and um, nobody's not quite sure what happened, but certainly one suggestion was it was constructive dismissal by the political leaders. Another suggestion was that some sort of resigned as a protest, with the intention that maybe they would realize they couldn't continue without him and invite him back, and so on. And anyway, he did resign. He wasn't invited back. Arup's nearly left as well, but yeah, and I think the Arup board was strongly considering leaving the project, and they decided to stay. Now, and a new architect was adopted, Peter Hall, to finish the project, which again was very controversial because the Australian Architectural Association, so on, really wanted Utzon to finish, and so Peter Hall had a bit of a tough job dealing with pressures and controversies from all sides. I must admit, looking at the headline there, plans Russia politics. That is correct. It was rushed for political purposes, and that did not help the cost overrun. So, looking at the roof design. The initial roof design was just freehand curves, with the assumption that membrane action would work. So you can see the dates there. 1957, the original competition entry with assumption single skin RC shell. And yeah, when the Arup engineers went to Utzon for the profiles, he just handed them the freehand sketches. Then sort of 58, moving into parabolic schemes. So again, RC shells with ribs. The louver walls at this point between the shells were envisaged to be reinforced concrete, so would actually sort of join the various shells together. Realized that wasn't working. So in 59, there was a further design with double RC shells. Then to 61, start looking at steel space frame for the roof. And you also note the louver walls were becoming stiffeners on the shells rather than complete walls in between. 61 again, steel space frame. 61 another scheme, so May and then June. Back to concrete. 61 June, back to space frame. 61 September, back to concrete. October 61, another concrete design, and another concrete design, and also in October. January 62, we get into the precast ribs again, and 62, 63, again, the final concrete design. Now, then so it started off with freehand, went to parabolic roofs, then went to elliptical roofs, then went to circular. Also bear in mind the roof height here is about 60 meters, so it is a fair size of building. So yeah, 7 separate schemes in 1961. Now, spherical scheme, apparently Arup did recommend the spherical scheme initially, was rejected by the architects, but then later on suggested by one of the architects, and that's when it got accepted. So what was significant about the spherical design? One of the big problems with the Sydney Opera House roof was actually constructing it. And they realized that precast concrete was the way forward. Otherwise it'd be a lot of working at heights with huge amounts of scaffolding and so on. And they realized that with a spherical scheme, where all the roofs were cut from the surface of the same sphere, meant that the double curvatures were the same in all directions. This also meant, therefore, that they could standardize the concrete sections that were used throughout the roof, and that they could use the same sections on all the roofs. So huge amount of standardization was achieved through the double circles or the spherical scheme. This is the roof structure. So the roof surface is actually tiles. These are all precast ribs, and you can see each of the ribs there all start from the springing point at the bottom, and they gradually widen as they get higher. And that is a constant, so the constant units across all the roofs, and the only variable is how high the roofs actually go. This means for there was only about a dozen different rib pieces used throughout, with some variation along the ridgeline, but basically several thousand ribs and cladding pieces from about 12 individual components. So it was post-tensioned both along the ribs and across the ribs, so both sort of radially and across, to give a shell-like behavior. So it's not actually a shell, but it has shell-like behaviors. And then also being spherical, the cladding was then precast as well, with all the tiling built in. That enabled them to do the tiling very high standards. Also, of course, the segmented construction meant that thermal movements could be accommodated much more easily. The analysis of the roof was difficult. So we're talking round about 1960 here, and there was at that point to analyze the roof. Well, hand calculations was going to be very, very difficult, especially with the shapes and complex geometry. So they worked on principle of physical models. So the very first scheme, there was a Perspex model built at 1:60 scale. And you note the Perspex model was built in Denmark, but then assembled in Southampton University for the load testing. So it used white perspex for the roofs, clear perspex for the walls, and covered all over with strain gauges and movement measurements and so on. And you can see there the actual physical loading was by weights hanging from the roof and then measuring the deflections. Testing was done by a young graduate called Bob Emerson, who subsequently went on to be Arup chair and with Clinton Tang, and supervised by another name, Peter Rice. So Peter Rice was a young graduate at this point as well, and his job was to supervise Bob Emerson and Clinton Tang on the analysis of this. So all the results taken from strain gauges, manual recordings, and what they found was the shear force between the roofs and the walls was huge. The deflections of the roof were huge, and so on. And they realized that that initial design just was not going to work. Image on the right. Also, the physical models used for wind loading. So that's the wind tunnel model on the right there. Now, physical models weren't going to work. Hand calculations weren't going to work. Well, at least not quickly. And the Arup team realized that they had to adopt this newfangled thing called the computer, which, had been around for about a decade and had been used in the aeronautical industry, but this was the first significant use on a building project. So, as Paul Am said, while some use of computers had been made at Arup in the late 1950s, solving large simultaneous equations and the like, this would be the first time that a digital approach would be the primary structural analysis. Also, Arup and Son said, it was clear in those early days that to achieve a solution at all, to make it possible to build the structure, excessive use of electronic digital computers was necessary. It would otherwise have been almost impossible to cope with the sheer quantity of geometric problems, let alone the complexity of the analytical work. Note also there, they described it as electronic digital computers. Electronic because in the 1950s, 60s, and earlier, a computer was not a machine, but a person. And you may have seen or from books and films like Hidden Figures, the computer room was a room full of mathematicians, quite often women, who were just there to crunch numbers. So an electronic computer was a machine to replace those mathematicians, and it was digital because also there were analog computers in those days. Analog computers sort of fell out of fashion in some point in the 60s or 70s, and they are around, but they are very rare these days. So each rib, as I mentioned, each rib is a tied arch joined at the ridge. They are loaded by self-weight, wind, auditorium ceilings, thermal loads, creep loads, construction stages. Now, each side of the shell was analyzed using the stiffness method, initially with a maximum of 18 nodes. But later on expanded to 35 nodes as computer power increased, and these would take their 5 load cases, which would run in about 55 minutes. The main shells as a whole were analyzed using the flexibility method. Again, Peter Rice to get involved. He was writing some of the computer code for this, and so each of the ribs was actually statically indeterminate, which the FE analysis couldn't cope with at that point. So they would make them statically determinate by adding redundant releases, analyzing for that, and then analyzing the effect of adding the redundant releases back into the structure, and then combine the results together. So So the lateral load on the main shells analyzed different methods, 136 nodes, in many cases, 5 load cases. These would take nearly 4 hours to run. In fact, the image on the left-hand side, you can see there, that is one of the analysis models of a rib, plus the temporary, the support frame that was used during the construction process to make sure everything connected. So 4 hours to run at the cost at the time, £1 per minute. So 4-hour run would cost £240. Now, if we were to take into account inflation, that meant that each run in today's money would cost £5,200. Now, yeah, in the moment, you could go out with £5,000 and buy an FE program for that. They had to write the programs themselves. And I mean, we say it takes 4 hours to run. Apparently, each run would, to do the run would take about 3 weeks to do the initial calculations, determine all the input data, program it into punched tape, and then the 4 hours run was just at the end, and of course, then all the numbers will come out, and you have to interpret all the tables and numbers. In comparison, I've got a GSA model of one of the Sydney Opera House shell roofs, complete model, 1,300 nodes, 13 load cases, runs in just 2 seconds now. So there's 60 years thereabouts. Speeds have improved quite a lot. Now, the shells get all the attention, but what I didn't realize was just how interesting the glass walls were. So glass walls, very complex shape, and an unprecedented design problem. So the glass walls, part of the design was done by Peter Hall, and these glass walls were required to close off the gaps between the concrete shells. These glass walls were hung directly from one of the ribs, and for the end glass wall, as you can see there over the restaurants, these walls had to come down. There was then a lower cone where the direct roof over the restaurants, and then there's a transition cone joining the lower roof to the vertical walls. Complex three-dimensional geometries, which difficult to do on a drawing board. Now, these designs, the idea was that, these were example with laminated glass for strength. Again, very new technology at the time, with manganese bronze bars and fittings connected to steel beams. Original Erzon design had plywood beams running on each rib, which the idea was eventually dropped, not least because the plywood beams would have been very, very deep and block out almost all of the visibility through the walls, the glass walls. So each rib hung from the underside of the roof, intersects through the 2 cones, and then connects at the outer wall. So each of those was a continuous 3-piece beam. And again, calculating each of those ribs was going to be quite difficult to do by hand. So the solution was, again, computerization. So this was very much the first example that I know of, certainly in buildings and possibly in total, about parametric design. So they wrote a computer program which would take the parameters of the 3 curved surfaces, calculate the intersections of those, calculate the lines of the ribs and their geometry, load the ribs, analyze the ribs, output the bending moments, shear forces, and axial forces on each, which would then allow them to be designed by hand in the traditional manner on calc pads. Second problem with the glass roofs was fabrication. So you may know, laminated glass is very, very difficult to cut once it's been laminated. You have to cut it first, laminate it second. And so the fabricators required detailed dimensions of every single glass panel on the walls. And of course, as you might see, that everyone, apart from the line of symmetry, everyone was unique. So part of the program as well was to calculate each glass panel and the 6 dimensions required for them to be fabricated and cut. So the four edge lengths plus 2 diagonals to actually give the geometry. In theory, you could get away with 1 diagonal, but of course, giving 2 diagonals means you then got the check calculation to make sure that it is actually correct. So timeline, how we doing? So stages of construction. So yeah, mentioned the construction of the foundations and the base part of the structure started in 1959 and was completed in 1963. Superstructure construction then started in 63 and was completed in 1967. And then the glass walls and fit out were completed in 1972. So the roof, look at the roof construction itself. Yeah, the roof consists of 2,400 precast units and 4,000 tile panels, which you can see there. These ribs were built in 4.6-meter lengths using the dozen profiles that I mentioned earlier. And this 4.6-meter length was the sort of the limit of crane capacity at that point. And even then, they had to do a global search to find tower cranes which had the capacity to actually lift concrete units of this size. These units were all factory made on site, so there was a the precast concrete factory on the site, and then the erection was done by 3 tower cranes. These tower cranes were built on tracks, so which could then be gradually moved across the site as the roof was built. And if I remember correctly, it was construction started from the city side and then worked towards the harbour. So each of these ribs were built on erection arches, so they're steel frames. They were then temporarily stressed. There was a computerized surveying system to check the coordinates of all the points to make sure everything was being built to tolerances. And once everything's placed, then everything was post-tensioned in both directions to full tension to ensure stability. And then once that was done, the temporary structures could then be removed. Also, then the prefabricated concrete shell tiling units could then be added as well. So yeah, the precast, the concrete cladding, these precast concrete panels had aluminium strips set into the concrete, which then positioned all the tiling, and again, these were also manufactured on site, so achieved sort of factory level construction, even though it was built in situ or on site. And yeah, while some feared that it would never be completed, it was completed in 1962. Marred in controversy, but finally opened in 1973 by Queen Elizabeth. And yeah, the public perception had turned around over the project life. Yeah. End results. So the recognition of the engineering achievement. So over Arup himself was received the RIBA Gold Medal in 1966, and the Sydney Opera, and he also won the ISRT Gold Medal in 1973. ISRT Special Structural Awards was also given to the Opera House in 1973, the precursor of our current awards, and it was also declared a UNESCO World Heritage Site in 2007. And yeah, public opinion has evolved. It is now, a cultural icon. It is a symbol of Sydney. It's a symbol of Australia. It is, internationally recognized. You just have to show the roof and everyone knows it. There were some initial design problems, particularly acoustics. And so Arup, the company has been involved with Sydney Opera House over the decades, including the updates that the acoustics, which I think were done about 10 years ago. So yeah, huge impact on structural engineering as well. Yeah, it pioneered the use of digital analysis and structural engineering, and indeed parametric design, computerized submissions, computerized surveying. So opening in 1973, the Arup Computing Group, as they were by this point, decided 2 years later to start selling the computer programs they've been working on. In 1970, no, 1976, that was 1976. Started selling. Now, in those days, consulting engineers were not allowed to advertise. And so the decision was made to create a brand for Arup software, which they called Oasis, Ove Arup Systems, which I am now a part of. So 16 years of design and construction. Yeah, I think it's fair to say the Sydney Opera House kickstarted the digital age of structural engineering. And yeah, that legacy lives on today. So yeah, Sydney Opera House, what was it? A political whim, a political football, a design could not be built, sacked architecture's 15 years of digital innovation, and now a globally recognized icon for Australia and for Arrow as well. And let's face it, its legacy and impact is immense. Further reading, the Arup journals. There's Arup Journal, so Arup Journal, which was published in 1973, which was also published. I think it was published in the contents of the Arup Journal was also published in the Structural Engineer first in that year, and then reprinted in the Arup Journal. Both are available online. There's the Arup Journal of 1968, which was a special on Arup computing at that time, particularly of the Sydney Opera House, but also many other projects that were involved, being worked on in the 1960s. And there is the sort of written version of this chat, which is also available on the iStruct website. Gosh, that was published a year ago. How time flies. Also, for that note, thanks to Copilot, Touch of AI, helped me put the presentation together. Said, there is the paper, suggest a presentation. His ideas were not brilliant, but it helped me. But gave me some suggestions, and I pulled it together. Yeah. Never use AI for the final result, but they can be very useful for getting suggestions. So yeah, and at that point, I will finish and say, are there any questions?
Thanks, Peter. That was an excellent talk. Building really is an amazing achievement given technology that was available at the time. I can see that there's already a question in the chat from Pat. So could we either put questions in the chat or maybe put our hands up? Would be great. So Pat's question is, roughly how many engineers were in the digital team at its height? And what was the split between software engineers and structural engineers?
That I don't know the answer of. I get the impression from the journals that the numbers were not large, and um, from what I know, certainly subsequently, um, the split was 100% structural engineers. Um, it's only in the last decade or so that pure software engineers have got involved with Arup computing. It has always been um, the civil structural engineers themselves learning computing and working on the software directly. For better for worse, certainly structural engineers working on structural software, they know what it's supposed to do. Computer software engineers, they have additional expertise in architecture, software architecture, and so on. And these days, it is a joint project between software, computer scientists and structural engineers. In the 60s, I'm pretty sure it was all structural engineers.
Thanks, Peter. Do we have any other questions? Would it help if I asked everybody to, or invited everybody to unmute themselves, maybe? We do that.
Yeah. Any questions? Any comments? Any observations?
I thought it was really interesting to see that it's really an early modern method of construction in terms of repetitive components and the off-site fabrication of the cladding. Really, it was quite ahead of its time, wasn't it?
Yeah. I mean, one aspect which I was quite fascinated with, maybe not so much the senior house, but certainly in the 1960s in the journal there, they talk about encouraging the engineers on the other projects to use the computer, but also before they were allowed to use the computer, they had to pass the gatekeepers. They had to demonstrate to the Arup computing team that they understood how the structure was working, and they had to present initial calculations the hand calculations to demonstrate that, and they were then allowed to use the computerization afterwards for the more detailed calculations. These days, it'd be good to return to that. These days, all the graduates access computers and they just do the analysis and assume the answers are right. Um, yeah, ongoing work to make sure, the grads aren't working in the vacuum. Oh, Mike,
Right.
got your hand up.
Can you hear me?
Yes, can you hear you, Mike?
I mean, obviously, I think in the blurb or whatever, it suggested these people were working in a cellar and in a monk's cell. But I just wonder whether, and it's a long time on now, what kind of feel you've got for how were they talking to other consulting engineering boffins, I'm going to call them,
Mm,
while they were trying to develop these. I'm going to, well, let's just say numerical models, calculations,
mm,
and how significant the people who are actually had the computer power themselves in influencing how the Arab team moved forward.
mm,
It's difficult to believe, despite the presence of what people might describe as geniuses uh, in the Arab household, that they could have, they wouldn't have spoken to other people about it.
mm.
And I just wonder whether you've got a feel for how much that they were able to benefit from other people's ideas as they move this thing forward.
Yeah, good question. In the early 60s, I'm not sure. I do know in the late 60s, there was certainly a lot of collaboration between the major consulting firms. Um, to produce software sort of together. And I know that, yeah, initially, yeah, to begin with, yeah, these mainframes were mostly at universities. Arabs took the decision that to actually buy a mainframe to put into the basement in the Fitzroy Street office, because they saw it as a worthwhile investment at that point. So whether all consulting engineers had the mainframes at that point or were renting out time on the universities, I'm not sure, but certainly late 60s. Yeah, the big consulting companies, especially in London, definitely in London at least, were talking to each other and sharing programs and sort of working together. That sort of society sort of whatever reason sort of changed, and by the mid 70s, everyone was doing their own programs, and hence Arup started selling the programs.
Thanks,
But
Peter.
that said, I mean, even now we've got I'm a part of the digital workflows and computational design panel. Should be the other way around, but never mind. And so there is a lot of discussion still about shareware, computer structural design analysis routines that people can make and share, and there is freeware and so on. So there is still a certain amount of collaboration going on. But there are also some quite big players in the market producing commercial software. So whole range.
A couple of questions in the chat, Peter.
Okay.
So we've got one on the complexity of the glass wall. It looks as if every panel was different. Is that so? And how on earth was the wall manufactured?
It was. Let me jump back to that slide. So yeah. So yeah. Apart from the line of symmetry, indeed, every single panel was different. So you can see in the bottom left-hand corner, there are the designs or the dimensions for 3 typical panels. Basically, the computer output would include all these dimensions for the fabricator to cut each panel out of the glass. And yeah, they'd be cut out, laminated together, laminated together, and then shipped to site. So yeah, the Arup engineers were actually basically submitting computer output directly with all these details on for the fabricator to put the glass panels together. Similarly, the steel beams were also computer design as well on those. So yeah, we've been very difficult to do without the computerization. That was.
There's another question from Sam Patterson.
Mm-hmm.
On the temporary support. So presumably the temporary support required the rib sections during construction prior to being fully assembled, and post-tensioned were every bit as complex and massive as the roof itself.
Yes, actually, I do have an image. Let me see if I can find a picture of that. I did. Yeah, there are. There's quite a few pictures I didn't include. So I'm just having a look. Let me see. No, wait a minute. There we go. Let me open that image up. So this is obviously a diagram or drawing. So there you can see the at least one of the halls with the tower crane on the track, and you can see there's the support frames at the ends of the ribs for the construction. So it looks like a sort of a triangular space frame. Haven't seen the detailed drawings on those, but that was what it looks. And then also some other temporary works underneath to keep things in position until it's all tied together.
Peter. Andrew has commented that he used computer analysis for hyperboloid cooling towers for Kia in the early 70s, and they also used software written by CGB, which ran on their own mainframe, with the input by entirely unforgiving punch cards.
Yes, I believe it. I never quite got to use punch cards myself. My brother, who's a few years older than me, did, and apparently, many stories of punch card blocks being dropped, and that sort of thing. Complete another try to put together again, and of course, yeah, you do all the punch cards, and then you get the results back and go, there's a problem somewhere with the cards, and I wouldn't fancy doing punch cards. I mean, they were a game changer originally. Was it there's a fascinating book called Turing's Cathedral, which is all about the creation of the ENIAC, the American programmable computer, which was built during the Second World War. And they were talking about using punch cards. I mean, punch cards for the input, but also punch cards for temporary data storage, where machines would actually be creating the punch cards for data and then read them back in again and so on. Apparently, a small run might use 1 million punch cards as part of that. So yeah, they were an impressive technology, but we moved on. I think the Arup computers were using punch tape rather than punch cards, or at least the ones I've seen were using punch tape, which I think has their own problems. Tape tearing, for example, and that sort of thing. Yeah, things have moved on.
Alistair Hughes has asked, doesn't John Hooper or Helmsley deserve a mention for his work on the glass walls, not least because of his recently published tome on the subject?
Interesting. I've not seen that tome. If I'd read it, knew about it, definitely. I'm intrigued. I shall have to follow up on that reference. My bits were taken entirely from the Arup sources, plus some bits from the Sydney Opera House website itself as well. They've got some of the history, and it is, where was it? There's definitely the original. There's a PDF copy of the original design, the competition entries brochure as well, which is available online on the Sydney Opera House website.
We've got another question from Kevin. I think you said that a modern analysis has been carried out using 1,000 or so nodes. Has a modern full analysis been carried out for the whole Opera House?
I don't know. I know that I've seen models of the individual roofs were done as part of the refurbishment or some work which was done around about 2000. I would say probably, but I don't know for certain. I mean, heck, if I'd been when I was a student, this would have made an interesting dissertation project, modeling the whole Sydney Opera House. So I suspect it's been done. I've not seen it.
Thank you.
Sorry to, could I jump in with a question?
Sure.
Sorry, I can't find the hand up button. So thanks very much, Pete. It's been really interesting. I was quite taken by the slide showing the evolution of the roof structure, and I couldn't help but think about fees. And I'm guessing there was like a river of fees flowing into Arups at the time. And I was wondering if if it was a very significant, I mean, I'm sure it was, but was it a really significant project for Arups at the time? You know, did it really help make Arups what it is, or did it nearly break Arups? You know.
Both. I think. Yeah, I don't know the detail, but yeah, I think there was definitely reading back through Arup's biography and some of the other papers at the time and everything. There's definite indications that it nearly bankrupted Arup. But yeah, didn't. And yeah, they came through the other end. And likewise, in the Arup, journal special, they talk about nearly dropping themselves off the project. It was, there may have been a lot of money coming in, a lot of people working on it. But it was, whether it made a profit or not, I don't know. I mean, subsequently, end result of it hugely different to the company. At the time, I think it was a squeaky bum time, as they say.
Andrews asked whether Ronald Jenkins, who had carried out calculations for the Bryn Mawr rubber factory shells, was still very active within Arups. Was he involved in the design and analysis of the roof? Do you know?
I don't know. I don't know. I remember the name. Yeah, there were a lot of people involved and a lot of projects going on as well. This definitely wasn't the only project. So possibly, but I couldn't say either way. I'm not sure. Yeah, that information might be buried in the archives somewhere, wherever they are.
Andrew has commented again. Jenkins was one of the partners.
Ooh.
Time.
So I'm thinking he might have got a name check in the yeah, I mean actually, thing to do is I suppose to have a look at the review the the two Arup journals. I think did he get mentioned in at least one of those? I can't remember. He might have done. But they're both available online. That's what all the Arup journals are available online. Freely accessible. Interesting reading. A lot more detail than I've gone into here. This is very much a nice high level summary. Each component will be a major presentation in its own right to go into full detail.
Thanks, Peter. Any more questions? Have you been to Sydney, Peter?
I have. Got to visit once. Must be about 10 years ago now. Visit the office there. I did have to do my pilgrimage to the Opera House. Yes, has to be done. Yes, fascinating. Didn't get a chance to go inside, unfortunately. But I must admit, at that point, it was just an icon. Subsequent research I've been doing on the project, I think I have a much better understanding of what it was all about. It's a fascinating project, difficult project. Yeah, I'd be very interested to go and revisit it now with what I've learned over the last couple of years on this.
Brilliant. Well, if there's no more questions, thank you very much again for an excellent presentation.
Pleasure.